Hi, I'm Mohammed Mehdi Hassan. I'm going to present the paper entitled CLFace, a scalable and resource-efficient continual learning framework for lifelong face recognition. As we know, existing deep neural network-based face recognition models, typically trained offline using stationary datasets, cannot adapt dynamically without complete retraining. On the other hand, retaining these networks from scratch on large datasets has several challenges such as high computational demands, limited storage capacity, and privacy concern. So, fine-tuning with new identities could be a potential approach in this case. However, this often leads the model to experience something which is known as catastrophic forgetting of previous knowledge, as the uh, newly trained feature space becomes biased towards the new task. As a result, several continual learning frameworks have been developed that enable a model to train progressively over time with only new batch of identities. So in a biometric identification system such as face recognition, an ideal continual learning algorithm should possess the following properties. First, it should handle continuous streams of batches with new and previously learned identities in any order. Second, it should maintain a nearly fixed number of parameters to keep the computational requirements and memory footprint bounded. Third, it should retain past knowledge while improving its feature representation capacity. Fourth, it should not store any exemplar, prototype, or prior models. However, unfortunately, none of the existing continual learning algorithms meet all these. So, in this paper, we introduce CLFace, a continual learning framework for face recognition that strictly follows all the essential properties of a biometric identification systems. It incrementally enhances learned representation through a classification-free architecture, and it ensures scalability by continually learning new batches of identities using a fixed network, and it provides exemplar and prototype free solutions for continual face recognition. This is the overview of the training and testing protocol of the proposed CLFace framework. Typical continual learning protocols evaluate models only on the same classes within the same dataset. However, in this work, we adopt a more challenging setting by testing CLFS on the unseen identities from both in-domain and out-domain datasets. Here is the implementation of our proposed CLFace algorithm. Let's consider that we train a model M sequentially on T number of steps or tasks. So within these steps, the identities may overlap. So at the incremental step t equal to t, we test our model MT twice to determine both the in-domain and the out-domain performance. To evaluate the in-domain performance, we test MT on the test set of the trained dataset. But to evaluate the out-domain performance, the model MT is tested across various face recognition benchmarks datasets. The figure illustrates the overview of the proposed CLFace framework for lifelong face recognition. It consists of a teacher model MT-1 trained on previously seen identities and a student model MT initialized from the teacher model. However, when a new face identity is fed to both models, we employ a loss MFSD, and this loss penalizes the drift in local feature maps between the student and the teacher models, helping the student model to retrain the learned representation. We also have two other losses, CKD and GPKD. GPKD constrain the student model to maintain a similar orientation to the teacher model embedding space, while CKD loss actually enhance the discriminative power of the student model feature representation. So let's talk about the objective functions. First, we have multi-scale feature distillation, and we employ this loss to transfer the multi-grain information from the teacher to the student model. It helps the student model to learn comprehensive knowledge. And a mapping function, we employ it a channel-wise average pooling. So this function uh, processes the 3D spatial feature maps to generate a flattened 2D feature map. Then, in this loss, we actually minimize the L2 norm distance of these spatial feature maps between the current and the previous models at multiple stages. We also introduce a lighter constraint on feature embedding to achieve an optimal balance between the plasticity and rigidity within our CLFace framework. So this geometry preserving knowledge distribution loss focuses on retaining the local geometry, particularly the orientation of the student model, normalizing feature embedding. In fact, it poses a constraint that prevents the feature embedding of the student model being entirely rotated. Finally, we introduce contrastive knowledge distillation (CKD loss), which enables us to learn discriminative feature by maximizing the mutual information between the student and the teacher model. It helps the student model to retain the learned representation during incremental learning. Uh, in each batch, the positive pair comprises the feature embedding from both the student and the teacher model of the same identity. So that's the positive pair, and other pairs are the negative pair. The total loss function is the summation of all these three objectives. Here is the training setup of our framework. As a biometric identification system, we need to evaluate our CLFace algorithm on both in-domain as well as on the out-domain datasets. And as a baseline, we also employ three continual learning training scheme. First, we have feature extraction, uh, which train the model on base identities and then extract features from the new identities in the subsequent step. Then we have fine tuning, which update the old model with new data that leads to the forgetting of the past knowledge, resulting in lower bound performance. Finally, we have joint training, which combines data from all learning steps, and this scheme provides the upper bound performance. So the figure illustrates the comparison of the proposed CLFace with other approaches evaluating on in-domain performance. As you can see that our proposed CLFace framework shown in blue achieves the highest verification accuracy across all these three datasets: WebFace, MS1, MB2, and BGG phase 2, whereas the fine tuning scheme performed worst in. So here is the comparison of CLFace with other baselines for out domain evaluation. Our method consistently outperform baseline approaches across all datasets. As expected, fine tuning scheme results the lowest verification accuracy, while the joint training scheme achieves the highest verification accuracy. We also evaluate our CLFace framework on the mixed quality benchmark IJBB, IJBC, and TinyFace datasets. We also investigate the effect of base training on our CLFace framework. Based on the data uh, from the table, we have several observations. So the performance of the CLFace significantly improves with the increase of the base data. For example, using 75% of the base data improve the performance than the 10% or 25% of the CLFace framework. So finally, in conclusion, we in this work we present CLFace, which is a scalable and a resource-efficient lightweight framework for face recognition. It outperforms state-of-the-art methods on unseen identities. across both in-domain and out-domain datasets. Thank you.